exactly you can work this. So the kind of problem I give you in the test or a quiz would be exactly this. I'd say find a power series representation for this function, like square root of x. Now tell me what the square root of 0.2 is. You know, something close to what you built it around. Cool? Exactly like what we just did. And this, sure enough, if you do this, you get, I can't remember how many nines there were, you get the same thing. Kind of nifty. All right. So as long as all your inputs are really close to 0, this polynomial works just as well as this function. That's kind of nifty. So let me give you this here before I get too drawn out here. One side is all about section 11.8, the power series stuff. And the other side is about this Taylor series stuff. One little thing, well, let me do one more example of these Taylor series, and then I want to point out something from section 11.8. Another really kind of nifty Taylor series to do is for e to the x. And officially what we're creating here up on the board are called Maclaurin series, because a Maclaurin series is just a Taylor series that has a equals 0. And historically, it's because this dude Maclaurin was working on series dealing with zeros, and Taylor was working on series dealing with anything. They both got the results roughly at the same time, so they both get credit, right? But a Maclaurin is just a specific type of Taylor. Maclaurin has 0 in for A. Taylor has anything for A. How we doing? Okay. So to create this guy's Taylor series, Maclaurin. Build it around a equals 0. Do it the same way, right? F of x equals e to the x. In fact, this is nice. Pretty much stop that at some point. All right. F of 0 is 1. F prime of 0 is 1, blah, blah. F n 0 is 1. So now f of 0 plus f prime of 0 x plus f double prime of 0 x squared over 2 factorial plus. So I'll get 1 plus x plus 1/2 x squared plus 1/6 x cubed plus dot dot dot. Can you guys see that? I just fill it in, and of course nothing cancels with these factorials because all these are 1s. So 2 factorial there, 3 factorial there, 4 factorial here. And what's a property of E, which some of you guys will realize we kind of built into it because we already used the fact that its derivative is equal to itself. When you take the derivative of this, you get 0 here, you get 1 plus 1/2 x squared plus 1/6 x cubed plus, okay, you pick up the same damn thing, right? And of course, this is the one that, this, how many terms are there here? How many total terms? Infinite number, how many total terms here? Infinite number, even though I lost one, right? It's the old thing about if you have a hotel with an infinite number of rooms and you have one more guest show up and they're all full, what do? Just have everybody move a room over. And then, so you can have 18 billion people, have everybody move 18 billion rooms over. You're fine, right? Sort of like that in reverse here, really. That's all side note. But now, what would this work for? We could do the same kind of thing. This should work for x values. If I stop somewhere, if I stopped here, it should work for x values close to 0, because that's how I built this. So if you do, again, if you do e to the, let's try 0.1. That should be equal to, roughly, if I stop, 1 plus 0.1 plus 1/2 0.1 squared, 1/6 cubed. Let's see if that, how close that gets, going out that far. Let's see. No, Jeff. Here I get this here. Probably 6's forever. So these agree out to that spot, basically, right? If I rounded it, they would agree out to one more spot. Cool? Kind of nifty. So the one thing I wanted to, I mean, do you guys get a feel? Say again?
How would you represent that as a series?
Which one?
The EVX.
Oh, well, that is this. This is the answer. This is what EVX is. Oh, as a in series form. Yeah, thank you. What would that be? Sum n equals 0 to infinity. X to the n over n factorial. I love it. So that is the power series for E. Pretty freaking nifty. Might just be me, I don't know, but I think it's nifty. So, do you guys get a feel? I mean, whenever I ask you to create a Taylor series or something, you do the same damn thing every time. The only thing that's going to change is the function. So the derivatives are going to be harder or easier, depending on what function I give you. I'm going to ask you to do it on n equals 0 or whatever. So you just plug that value into the function, the derivatives as they come, and then you throw it into the general form. I think last semester I gave the form out, even though it's really not that difficult to memorize. Right, the pattern is very obvious. The one thing from 11.8 that I forgot to mention is actually, if you look at the handout I gave you at the power series side, right in there, right in the middle, fundamental problem for what values of x does a given power series converge. So for each of the ones we've done so far, we could take that x to the n over n factorial. How could you figure out the interval of convergence? What would you do to that? Might actually be a good thing to do. If I have, figure out the interval of convergence. Of course, if you missed last class, that sounds like some kind of weird religious cult or something, but don't worry, I'm not going to give you any Kool-Aid to drink. I have this here. How do I find that guy's interval of convergence?
Ratio test?
Ratio test, exactly. I almost always use the ratio test unless it's some nth power deal, and then I use the root test, right? Limit as n goes to infinity. There's no negatives in here, so I'm not going to worry about the absolute value. What do I put first? Good, the n plus 1 term times the reciprocal of the nth term. Well, I do need the absolute value on because I don't know what x is. And this equals what happens in there.
X to the n.
There's an
X.
Yeah, the x to the n's cancel out. So you get 1x left up top. And you get what left for the n's?
N plus 1.
N plus 1 left over on the bottom, right? Because this is n plus 1 times n factorial. Those cancel. So sure enough, as n goes to infinity, this thing goes to 0. That's the case where the interval of convergence is, I don't know if we hit one like this. Did we hit one like this? I think we did. So that, I think, yeah, we definitely did. How do I interpret the results of the ratio test? It just has to be, less than 1, exactly. It's got to be less than 1. That's always less than 1. So what values of x work here? All values of x. That's always less than 1. So the interval of convergence is infinite. So last time we saw an interval convergence, I think we had one that was like from -9 to 1 or something. So it could either be all real numbers work, or it could be some from something to something. And the last possibility, the thing that I've kind of gone this a roundabout way, but the thing I want to tell you from 11.8 that I didn't cover last time, a really easy example would be this guy. Which one, Jeff? I don't know. What would work here? Right, just use the one that's on there. Yeah. So if I try to test this guy, the limit as n goes to infinity, so the n plus 1 guy first, divided by the n guy, right? I didn't really have to set up separate things because it isn't really a fraction to begin with. We can just divide it directly. What's left over here is there's an n plus 1 left alive and an x left alive. So when n goes to infinity, is there any x that I can plug in that's going to stop this guy from going to infinity? Yeah, the only thing I can use. So this limit is infinity. It's an infinite limit. So the only possible x that can dampen that from happening is 0. So the only thing x can be is 0. So the interval of convergence is 0. The radius of convergence, which I don't know if I talked about before, is going to be 0, right? There's no radius. So the interval of convergence is just 0. I mean, that's the only thing that could possibly work in this. And then it's a very boring freaking sequence. 0, 0, 0, 0. So there's only 3 possibilities. Either everything works, a select few things work, or only 0 works, which very often in math is called the trivial case. And in this case, you see why it's called the trivial case. Well, yeah, if you add 0 up, you get 0. That's amazing. So it's a very trivial case. That's the only thing that works. Cool. Okay. So what I want to do is, we actually basically got through everything I wanted to get through in 11, to tell you honestly. So what we're going to do next time is I'm going to have the answers to this. Obviously, next time I'm also going to have like a study guide, like I did last time, and the next week I'll have the answers to that thing, just like last time. But I want you guys to try. Now on the back, hopefully with what we talked about in section 11.9, you can see what to do with the last bits of this. So like the first 3 examples, which is find the nth degree Maclaurin polynomial for ln of x plus 1. To interpret that for you, I'm just asking you to find Maclaurin means a equal 0. And the polynomial now, I can call it a series, but I can also realize that it really does end up being a polynomial. So those are, in a way, those are interchangeable. There's a little bit of, you got to be careful on some functions, but most functions are the same thing. So 1, 2, 3, that's just like what we did today, right? Doing those, and then I ask you to estimate the value of blah, blah, blah. But the second set of examples, 1, 2, 3, those are the ones that, like number 2, part A, I ask you, if we already know that sine of x, is that, right?
Yeah.
Then what's sine of 2x?
2x minus 2x.
Right? Just plug a 2x